Okay. Hi guys. So today, I want to spend some time talking about the axiom of choice, but I also wanted to kind of take a detour, and this is something that I won't test you on, but I think I hope you might find it interesting. So we'll just spend like the first little part of class talking about this topic called ordinal numbers. Okay. So if you just want to take a break for half an hour, you can. It's up to you. The idea of this is that, of course, we can count. And let's remember how we count. Well, we start with the empty set. Then we have the empty, like we add 1. We add 1 to that, we get 2. We add 1 to that, we get 3. And this is how we add 1, you know. When we get to 10, oops, like that. Then we keep on going. Okay. Of course, and now the idea of an ordinal number is that what happens if you just keep on going? Like you don't stop at 9, you just keep on going. And in fact, this is the same as the union of all the natural numbers. Okay. Okay, and then the idea is that we don't have to just stop counting at finite numbers. We'll let ourselves like keep on going. Okay, so this, we'll call this a number 2. We'll call this the number omega. Sorry, my omega is not so good. Okay, and this is kind of what you get. This is kind of like the limit of all the natural numbers, right? Because you just keep on adding in the next natural number over and over again. If you just, so you call that the ordinal omega. And then what's interesting is that you can keep on counting from there. You can look at omega plus 1. Well, that's just omega union, the singleton of omega. In other words, it's like 0, 1, 2, keep on going forever. And then you have the natural numbers, also an element of omega plus 1. Or if you want to put it differently, 0, 1, 2, go on forever, and then you have omega. Then you can add 1, you could look at omega plus 2. Is like that. So this is the idea that you don't have to just stop counting once you run out of natural numbers, just keep on going. Okay. So if you keep on going, you get omega plus 3. You get omega plus n for any natural number n. Well, first you have the natural numbers, Then you have all the way up to omega plus n minus 1, say. Well, you can keep on going like that. And what you end up with is you have another limit. You have omega plus omega. Make that to be 2 omega. You know, that's just like you have 0, omega plus 1, omega plus 2, and on like that. Well, starting from 2 omega, then you can keep on adding to that, you know? You get 2 omega plus 1, 2 omega plus 2. That forever and ever, eventually you get 2 omega plus omega. In other words, you get 3 omega. Well, if you can get 3 omega, you can imagine that you could also get 4 omega. If you can get 4 omega, you could also get 5 omega. And everything in between. Well, eventually you get like omega times omega. Okay. And each of these things that I've listed has a kind of a special property. All the elements of each of these numbers are also subsets. So remember, for the natural numbers, if m is less than n, then actually m is a subset of n. Right? Because how you know this is like from one of the assignments, it's because n is equal to the set of all natural numbers m that are less than n. Okay. Okay, and then if I have n prime, that's the set of all natural numbers m that are less than n prime. N, then every number that's less than n prime is also less than n. Then you can show that actually n prime is a subset of n. Okay, so and then if you kind of continue this idea, well, you define omega. This is kind of like this is the set of all the natural numbers. So these are the m's such that m is less than omega. And then omega plus 1 is also the set of m's such that m is less than omega plus 1. And what are the things that are less than omega plus 1? Let's just 0, 1, 2. Then omega is less than omega plus 1. Okay. Okay. So let me tell you about just the main ideas behind ordinal numbers. The idea is that you can they have this property that any element is also a subset. So if lambda is an ordinal number, and omega, and let's say mu is, so if lambda and mu are ordinal numbers, and mu is less than lambda, well, we'll keep the less than be the same. Less than just means is an element of. So if mu is an element of lambda, then mu is actually a subset of lambda. Okay. Another of the properties of that the ordinal numbers have is that any ordinal number is a set of all the numbers which are less than it. Okay. So more properties. Well, there's kind of like two ways to get a new ordinal number. One way is to just add one. Okay, so this is the third property that they have, that if lambda is an ordinal, then lambda plus one, which is just all the elements of lambda with a singleton lambda, is also an ordinal. And then 4, if I have if S is a set of ordinals, then union of S is also an ordinal. And this is what lets you, so to count, you can either add one or you can kind of take a limit, and that lets us kind of extend things. I don't want to get into too much details with this, but it's just the idea that you know, you can count by adding one, but you can like keep on going. Now there is a like good reason to do this. So basically the applications, well, just applications to set theory, but you can use this, you can prove you can use ordinals as cardinal numbers. Well, if you use the right ordinal. Okay, so this is just a minor point, but if you remember the definition of a cardinal number, we said that like we needed corresponding to A. If A is a set, then we had this thing called the cardinality of A, and we just assumed it has certain properties. One application of ordinals is to use some of the ordinals as these kind of representatives for size. Okay, so that's one application. Another application is this thing called Trans-Finite Induction. Okay. So sometimes you need to have like an induction type of argument, but it's not good enough to just have like a statement for every natural number. You need something like you need to count a lot higher than that. Okay, so there's this thing called trans-finite induction. Okay. Another application uses the fact that if lambda is an ordinal, then every non-empty subset of lambda has a least element. Okay. In other words, the ordinal numbers are all well-ordered sets. And sometimes it's useful to know that you have a bunch of these well-ordered sets. Okay. So I just wanted to tell you like the reason why I wanted to just mention these things is because, so the next topic is axiom of choice. And when we talk about the axiom of choice, I'm just going to briefly mention that there's certain things you can prove using trans-finite induction and things like that. So I just wanted to give you an idea of like, you know, you don't really, there's no rule that says you have to stop counting with just the finite numbers. You know, you can, you know, keep on going if you want. Okay. And just as I mentioned before, I won't test you on any of this. I mean, I've barely given you any real information. So, okay. I just wanted to let you know that these kind of things are out there, you know? Okay. Okay, so let's start with axiom of choice. This for about 10 minutes and then we'll take a break. Okay, so our idea, so if A is non-empty, that just means then there exists an element in A. Okay, well, let's call it A0. If A1 is non-empty, then there exists A1 in A1. Okay, and this is just the idea that from a non-empty set, if a set is non-empty, then I can choose an element from it. Okay, and just keep on going. Okay. Okay, so now the question is, Can I find A0 and A0, A1 and A1, and AN and AN, as long as these are all non-empty? And the answer is kind of like, not surprisingly, yes. You know, I think you can prove this by induction. Okay. But now the problem is, this seems fine, you know, like, you know, if I tell you that I have two non-empty sets, I expect you to then tell me, well, you can like pick an element from each of them, you know, and there shouldn't be any argument about that. But now the problem is that I can just like adjust this a little bit, and now we're gonna have some disagreement, well, possibly. Okay, but if A0, A1, A2, AN are non-empty, can I find A0 and A0, A1 and A1, A2 and A2, AN and AN, and then on and on? And the answer is like, I don't know, maybe. Okay. Okay, so I guess can anyone tell me a reason why I should be able to do that? I'm actually not looking for any deep reason. You know, like it just seems so obvious. Well, sometimes you don't think about it too much. Seems like you just should be able to. So one reason for doing this, for being able to do this, might be like, yes, well, you just do it. And that might be like a reason for the statement. The reason against, no. Well, the problem is that like, you know, this kind of this induction argument tells you that like at any step of the way, you know, you can find an element in each non-empty set, but it doesn't mean that I don't know, just roughly, you know, you don't only need to find it at each step of the way, you kind of need to find it at all the steps of the way, kind of all at once. So the reason against might be no. You know, choosing one element from a non-empty set is fine, but now I'm asking like, pick one out from each all at once. Like you can't do all those things. You can't do so much. I'll just put like in quotations all at once. That's just a rough reason. Okay. Okay. Okay, so what I'm trying to say is that it seems like you should be, it seems on the surface that it should just be fine to do this. But in reality, we really need an axiom for this. Okay. So first, before we go, let me define. This kind of is a representation of something called a choice function. So let me define a choice function. Okay. Let X be a set. A choice function for X is a function F. The domain of F is X, and F of A is an element of A for all A in X, with A not the empty set. Okay, so basically a choice function is we have a set with a bunch of sets inside it, and we want to choose an element of each set in our big set. Okay, as an example, X might be all these A0, A1, A2, so on. And we want to choose, we wanted to choose an element of each AI. So you just choose an element of each AI. Okay. So we have a set of sets, like a set whose elements are all sets, and then we want to choose an element of each element. Okay. That is what a choice function is. Okay, so let's take a break until 3:40. Then we'll talk more about, we'll talk about the axiom of choice.